Hello everybody, welcome back to lesson 2 of the functional Python series, where I will teach you all about functional programming in Python. Last episode, we went through why functional programming was useful, and you can see currently on the screen, we discussed the 3 pillars of functional programming. So if you don't know how that works or what that even means, please go watch the last video. This is part of a series again. It is linked in the playlist. Alright, today we'll be talking about Lambda Expressions, a core fundamental concept of functional programming that builds on top of these pillars that we discussed, specifically a pure function and immutability. So let's begin. Alright, so Lambda functions. You might have seen them before, but you aren't really sure how to use them, or some people might have said Lambda functions are anomalous functions, which is true. For example, normally, let's say we want to increment a value by 1. So we can just do increment by 1, and then we can do something like this, and we return x plus 1. This can be a normal function. You can call it, you can do inc1, and then it'll just increment by 1. So this is a normal function with a actual name. Now, an anomalous function is a function without a name. It's meant for a quick and easy way to basically do some functionality, but you don't need to reuse it. For example, that same increment by 1 can be used with Lambda functions, which you just do this, and there we go. This is a Lambda function. Now, if you want to call the Lambda function, let's say we put it in a print statement, we do this, and we pretend, usually, let's say that inc1 goes here. This is how you will call a normal function like this, and then you will just print that. But again, since the Lambda function is anomalous, there's no name for it. We can remove this inc1 and replace it with the Lambda function like so. Now, what this will do is it will actually use the Lambda function as the actual value, and x is the parameter. You can see is to the left of the colon, and right of the colon is the expression. Now, I'll go over in detail what the expression means and stuff, but you can see once we run it, it outputs 6, just like a normal function would do. Now, I will say something about Lambda functions because we say that it's anomalized, but in fact, you can actually assign a name to it. So it's kind of a lie to say that it's completely anomalous. For example, we can do something like this. Let's say we can do a factorial function by doing this, by accepting a lambda with an x parameter, and then what we can do is we set this fact function to the factorial. Now, factorial is a special function because it involves recursion. So I'm going to go over how to recursively define lambda functions as well. But let's just remove fact for a second, and let's just say something like square. For example, the one that we defined earlier, which is a pure function. Now, all lambda functions must be pure. They cannot set values. There's no for loops or anything. So they must be pure. Now, what that means, again, please watch the last video, or you can just see up here. But again, just watch the last video to see what pure function means. So what you would do in that case, you would define like this, so that it looks like square equals lambda x, and then you square that. To call it, you would do the same thing as normal. Now, I kind of defined square up here. So let's do something like lambda square, so that it doesn't conflict with the file. I mean, the function name I defined up here. So yeah, you gotta be. So this currently is not actually a variable; it's a function. Just like the higher order function we defined last time, add increment by 5 is not actually a variable. It's a function wrapped in another function, and therefore when we call this, it will run as a function, just like any normal function. So same thing with this. We can actually use this higher order function in lambda later. But currently, if we do this, you expect it to print 25 because, again, it is a lambda function. Now, back to my factorial example, because we can define a lambda function like so, what we can do is we can do lambda x, and then what we can do for this is we can call the factorial function like so, and then what we can do is, alright, so before I actually call the factorial function, I have to show you something that we can do with conditionals with lambda statements, because what we can do is we can actually add a conditional within the lambda statement, but only if it's ternary. So I mentioned previously, we can't do stuff like setting variables in lambda functions because it must be pure, which means that it would not cause any side effects as displayed up here, which again, please watch the last video, because I'm not going to say that anymore because there are so many things that are dependent on the previous video. So if you, whenever I refer to pure functions, just basically assume that the function must have no side effects and all of that will be explained. So without that, I will just say this is pure function, which means that we can only do stuff like, again, ternary if statements, which, let me refresh you, is basically something like a statement if something equals or just if conditional else other statement. So that is the structure of a ternary if statement in Python. Now what we can do is we can actually embed this inside of Lambda because it is considered pure by the Python interpreter. So what we can do for the factorial function is we'll set it to 1 if x equals 0, else x times fact x minus 1. Now, this is the equivalent of doing this. Let me just show you right here. So this is, we can do something like if x equals 0, return 1, else return x times fact x minus 1. So these are exactly identical. Now, as you notice for this factorial function here, this and this square function are both pure functions. So again, please make sure that your lambda statements are pure. Now, what this will do is it will recursively call this factorial function. So once we do something like print fact 5, it will successfully print the factorial 5, which is 120. Now, obviously, be careful with the recursion call stack limit, the recursion size as well. Those still pertain with lambda functions. Don't think you can circumvent that. But this is actually a pretty neat method to basically recursively call anything. Yeah, yes, this works with Fibonacci as well. Now, Fibonacci is kind of a bit complicated because it involves something that we can do without the pure function paradigm. So let me show you what it means. So normally, Fibonacci, you'll have to set some things with a certain value for the Fibonacci sequence to work. But we see from the lambda function that we can't really set anything. However, there is a slight trick we can apply to basically set stuff within a lambda function. And that is within the default arguments list of the lambda. So for example, if we do a Fibonacci lambda series, what we can do is we can set a parameter, but we can also set something in the parameter as a default value. For example, I set A to a default value, I can set B to a default value, and I can set C to a default value. But this all must be within the left side of the colon. So the right side of the colon, there should be no setting or modifying variables because it violates the pure function. So this you can do. And let me show you something cool right here. Combined, again, with recursion and a ternary if statement, what we can do is we can do something like, think about Fibonacci and how it works. Normally, you'll do fn minus 1 plus fn minus 2. So what we can do with this is we can modify the default parameters around here. And again, the default parameters, they take in the parameter or they, again, resort to the default value. So what we can do with the default parameters, we can use these as base cases. And again, this doesn't mean that A is hard-coded to 1. Once you pass in A again, it will basically work again for later values if you actually pass in A as a parameter. Only if you don't pass in A as a parameter, that's when, again, it will resort to the one default statement. So what we can do for here is we can do A if basically C is greater than N, which is the nth Fibonacci term. else we can recursively call, but this time we will use, again, the new values, and this will override the default statements. So this will effectively calculate the nth term of the Fibonacci sequence. So we can do something like print, just fib of 5. And obviously, let me see what I did wrong here, because it's not supposed to print 1 here. Again, this is some debugging we have to do. So A, and then it adds on. Oh, yeah, we have to pass B into A out. Again, this just proves that there isn't any predetermined script I'm reading off. I'm doing this live with you guys, and hopefully if you see this, we can debug together. So yeah. Anyways, so yes, that is the 5th term of the Fibonacci sequence. Now what we can do here is, let me just show you that this works for a lot of Fibonacci values. Now obviously Fibonacci, the recursion does not work as well. So let me just do it for 10 values. So again, what we can do is we can pass in the Fibonacci sequence, and then we can do a range, which is an iterator, and then do something like that. And you can see I forgot to cast it to a list, so that is an issue. And you can see it works. 1 plus 1 equals 2. 1 plus 2 is 3, and so on and so forth. This looks pretty familiar, right? All right, what did I just do with the map function? I did that on purpose. That's right. That is a sneak peek for the next episode. So if you are keen with your eye, you might see what the map function does. But if you don't know what that just did, don't worry. You will learn it again in the next episode. So that's just kind of a sneak peek. But you can see the map function, again, it's also a functional thing. That is a pretty useful function. We'll be going all over how map works in the next episode. Now, there's another way we can do a Fibonacci sequence that recently popped up in Python 3.8 with the introduction of this operator you might have seen before. Again, as of this episode recording, Python 3.8 supports that. So, what we can do is we can set Fibonacci to be equal to the lambda. This time we can use a different statement. Basically, what we can do is, if x is less than or equal to 1, we, again, after 1, the Turner if statements, please remember that the statement you're running within in the correct condition goes before the if statement. So that's kind of like one thing you have to remember, because normally if statements will be a colon and then you type whatever you want, but for the ternary, you do whatever you want before the if statement. So right now we're saying if x is less than 1, we return 1. Also, another thing I forgot to mention about lambda statements is that they always return stuff. Okay, so there's no such thing as setting a void function. If you are familiar with, I know Python doesn't have a void function, but in other languages, lambda statements are never void functions. So you can't do something like in place, add and subtract, or modify array with pointers. That doesn't work with lambdas. Okay, so you must return something. So just remember something like this. So define lambda. I know that's a reserved keyword. Let's just do this. And then, okay, and then whatever you put inside the to the left of the colon. So like, let's say a equals 1, and then b. This will be equivalent to a x. A equals 1. Actually, you have to put a equals 1 at the back. So b, a equals 1, and then return whatever this is. So just imagine lambda as a single line return function statement. So just whatever you're thinking about writing lambda function, put this at the beginning as the parameter list, and then everything after the colon, just imagine, can I do it within one return statement? If not, for example, if I'm doing something like, a equals 0, and then if a less than equal to 1 or something, that is violation of lambda, and it will not work. So just imagine if you can just do this, and then expression. If this expression can work with this return statement, basically, it can fit in lambda. So for this, what we can do is, again, Turner if statements work if we do something like if x less than equal to 1, else 2. You can see that there is no difference here, this line will work. So again, that's kind of like my trick. If you want to write lambda statements correctly, you will just remember that, can I do it within one return statement? If so, then you're golden. All right, so back, let's remove this here. Back to the Fibonacci sequence with this new Python 3.8 definition here. What we can do is we can do, again, with the ternary if statement. This time, instead of calling if statement Fibonacci one time, we'll have to call it 2 times, which if you look at the recursion tree, it is absolutely horrible in terms of runtime complexity. But that doesn't matter because we're just demonstrating stuff. So yeah, let's print this out. So I just introduced you to both recursive lambda Fibonacci sequences, and the first one is obviously the more efficient one because it only calls Fibonacci one time. But that utilizes the cool hack with the parameter default statements and stuff. This is purely lambda. You can see there's no default statements, no equal, just pure function. So yeah, that is in fact the 10th Fibonacci number. So yeah, so that is lambda statement. Now finally, what we can do with this lambda statement is we combine this with our previously learned higher order functions, which is we learned that last episode there. So instead of actually defining a whole nested function like that, what we can do is we can do something like, let's say instead of higher order add, which is what we did last time, let's do what we do, higher order multiply, there we go. My spelling game is weak. Anyways, so we can pass in the multiply function. Again, we are talking about higher order functions here. So we can pass in functions. You can see functions that can take in other functions as parameters. Yeah, remember? So that we can pass in. But instead, we can do is we can return, instead of returning obviously a whole function like the one above, let's just return a lambda function. And this is short and concise. X times multiply. There we go. And then how we can call this is we can do something like print. Okay, so this is actually pretty cool. So with the lambda function, it's anonymous. Basically, you can kind of just define functions on the side. So let's say that we want to multiply by a order of 6, right? Or 7. Let's just do multiply by order of 7. So we can do multiply, and I'll just do multiply by factor of 7. Now this is a super long function name, but I'm kind of demonstrating something right here, so it doesn't matter. So what we can do is, again, we can do higher order multiply by 7. And then this doesn't multiply 7 itself. It's basically saying, okay, higher order multiply, spit me out a function that can multiply by factor of 7. So it would be more, I guess, useful if I say something like factory. I know, okay, before you guys flame me in the comments, factory is a OOP like pattern and stuff. So, you know, it's not really appropriate to use it like here in functional programming. I get it, okay? I get it. I know what factory means in OOP setting. But what I'm trying to demonstrate here is that this higher order multiply, for people who don't understand, again, higher order functions, sometimes they're hard to understand. So by putting factory here, what we're doing is we're basically saying, oh, this function creates new functions, and hence the lambda return statement. So we're just kind of like passing in a factory. So, okay, tell me, give me a function that can multiply by 7. So, boom. This is now the function generated by that factory function. Again, not the same as OP, so different, just to be clear. And now what we can do, just like above, is we can pass this in here. And now we can do another function, for example, 5. Now it will be 5 times 7. So, again, another debug moment. It's time for debugging, as everyone said. accidentally just returned the multiply. It's supposed to be x times multiply right there, just so you guys know it was right here. Alright, now it should work as intended. Again, 35. So you can see lambda statements work well with both itself and higher order functions. And again, higher order functions have been gone over last time. Same thing with this. Again, increment by 5, it creates a new function, and then that function is then used on for another function. So I kind of imagine it as its little function factory, but again, that is different from the OOP factory. So don't get those two confused there. But anyways, that will be it for today. Hopefully you learned something about lambda expressions, and I will not go into lambda calculus because that is a whole other thing of itself. But if you're wondering, that's kind of how lambda functions came to be. So just Google lambda calculus and have fun there. But next class, we will be going over the map function, which is, again, very useful as you saw with that sneak peek. Hopefully you enjoyed this video. Please leave a like and subscribe, and I will see you in the next one. Peace out.